Hello, this is Charlene. In this video, we're going to be talking about the complement rules of probability. The probability that an event E will not occur. The key word there is not occur. There are several ways to talk about the notation. This textbook says P of not E is equal to P of E bar is equal to P of E prime. But I want you to understand that the notation can differ from one website to another, from one textbook to another, but it all means exactly the same thing. So we're going to talk about that briefly right quick, the notation. Okay, so we have these are basically the shortcut symbols. And then here's how you would pronounce each of those. And then here is kind of a shortcut as well. Okay, so the first one is P of E prime. We pronounce that the probability of E prime, and I tend to say it with a shortcut P of E prime. So P of E prime. Then we have P of E bar. It is the probability of E bar. And the shortcut that I like to use myself is P of E bar. Then we have this third way of notating it, which is not listed in this particular textbook, but it is out there at a lot of websites and other textbooks. It's the P of E complement, which is the probability of E complement. And again, I like to shortcut it by saying probability of E complement. So the probability of E complement. Okay, but all of these mean exactly the same thing. They essentially mean the probability of not E, or the P of not E. That is the whole foundation for the complement. The complement is not E. So going forward, hopefully you'll begin to understand practically what this means. Okay, we've talked about the notation for the complement rules, but now we're going to talk about specific complement rules. The P of not E plus the P of E equals 1. P of not E is equal to 1 minus P of E. And P of E is equal to 1 minus P of not E. So what does that mean? Well, we're going to talk about it in terms of dogs and cats. So if I have one group, one big group, and in that group there are dogs and cats, well, then all the dogs and cats would add up to the total number of dogs and cats in the group, right? So let's write it like a math problem. So I've got some dogs, I've got some cats, and if I add all these dogs together and the number of cats together, it will equal how many dogs and cats are in one whole group. Now we've turned it into a math problem. Let's solve for the dogs. Let's say minus cats on both sides because we're going to solve for the dogs. So minus cats on this side. Order of operations says I have to do it to the other side of the equal side. So minus cats on this side. These cats are going to cancel out, and that is going to leave me with dogs are equal to one whole group minus all the cats. Okay, now let's think about this. Are dogs cats? No, they are not cats. So could we technically call the dogs not cats? Yeah, we could. We could say dogs are not cats. So then we could say not cats are equal to 1 minus the cats. So I want you to see that there's a little bit of a correlation here. So not cats, here's not E. Here's 1 minus cats and 1 minus E. So there's a correlation. It's like if they're not cats, then the dogs would be equal to the whole group minus all the cats. Or if we have the one whole group, we take out all the cats, that would leave us with all the not cats, which also happen to be dogs. Okay, so I know it seems a little bit convoluted, but it's going to make more sense here in a second because we're going to now talk about this in terms of numbers because probabilities are just numbers. So if we have the probability of not a cat and the probability of a cat, those could be just numbers. So for instance, it's like 40 or 0.40, let's say that there's 40% chance that these are dogs, and there is a 60% chance that these animals in the group are cats. Well, what does zero point 0.4 plus zero point 0.6 add up to? It adds up to one whole group. And of course, going back to the whole concept of probability, is that probabilities always add up to 100%. 100%. So 100% of a pizza means one whole pizza. So probabilities will always add up to 1. So if we have a probability that's say 4/6, and it's going to add up if you have two probabilities, two parts to your group, then it's still going to add up to one whole 100% of the group. And so that means that this that's added to it would have to be 2/6, because 4/6 plus 2/6 equals 6/6, and then 6/6 is equal to 1. So this idea that we want to convey here is that complements always add up to 100%. So whatever this probability is and whatever this probability is, it will always have to add up to 100%. So if you are missing, say, this probability, well, how would you find it? Well, you would take the whole thing, you would subtract this part, and it would leave you with this missing part. So this is how complements work. They will always add up to 100%, and if you're missing one of your probabilities, you can actually find the other one by subtracting it from the whole. Okay, we are going to work a couple of problems in the rest of this video to demonstrate how we can use the complement rule. This problem says that the table below shows the distribution by age of a random sample of 3,000 American moviegoers aged 12 to 74. Use the distribution to solve. Okay, so they tell us up front that there are 3,000 moviegoers in this table. So we've already written 3,000 here. And that's important because that is the total. That will be the total part. Remember, our probabilities are always based on a ratio that's a part out of a whole or a part out of a total. So that's going to be important that we know that 3,000 number. Here it says, if one moviegoer is randomly selected from this population, find the probability expressed as a simplified fraction that the moviegoer is not in the 45 to 64 age range. So how can we write this? They're saying find the probability that the moviegoer is not in that. So we could actually write that as the P of not 45 to 65 age range. We need to think back to our complement rules. Our complement rule that matches up with this, if we have the probability of not something, well, we need to use this right here, the probability of not some event, not that it's in the 45 to 65 age range. And so this gives us what we need to set it up. So we can write that as the probability of not in that range is equal to 1 minus the probability that they are in the range. 1 minus the probability that they are the event. Okay, so that means that we are now going to have to find the probability. So that's a part out of a total. So we could rewrite this as 1 minus, well, what is the part? Well, the total, we know the total because they already told us the total number, right? The total number of people in this survey were 3,000 people. So we're talking about not 45 to 65, but right now we're going to find the probability that they are in the 45 to 65 degree or 65 age group. So the 45 to 64 age group is 840. So that is my part. So it's going to be 1 minus. So the probability that they are not in this group is going to be equal to 1 minus this probability ratio. Okay, when I go ahead and put that into my calculator, it's 1 minus alpha f1 to get a fraction function, 840 in the numerator, arrow down to the denominator, 3000 in the denominator, and that gives me a final probability of 18 over 25. So this is going to be equal to 18 over 25. So the probability that the moviegoer is not in this age range is 18 over 25. Now, right before we go to the next problem, I want to point out one extra thing here. So the number 1, this is 1 minus a fraction. When you add or subtract fractions, you have to have like denominators. So we could have set this up as 3,000 over 3,000 because that would be 100% of my survey group. One whole group would be 3,000 out of 3,000 minus 840 over 3,000. There's common denominator. I can subtract those and it would give me this not reduced fraction and then my final reduced fraction. So again, the answer is 18 over 25. Okay, the next problem that we're going to do to demonstrate our complement rule is to find the probability that the moviegoer's age is at least 25. Well, we can write that as the probability is at least 25, but it doesn't sound like our not, the complement. We got an event and we got a not event. So at least 25 doesn't sound like that. However, let's look at our chart. So does the 12 to 24 age group satisfy at least 25? No, it does not. Does 25 to 44 satisfy at least 25? Yes, this satisfies the probability we're looking for, at least 25. Does 45 to 64? Is that also at least 25 years of age? Yes. And 65 to 74, that also is at least 25 years of age. So the only age that they do not want is the age that's between 12 and 24. So this becomes our not event. The only thing that they do not want is that age range. They want everything 25 and older, but they do not want the 12 to 24. The only age left out is 12 to 24. So that means that we could actually rewrite our probability. Instead of saying probability of the age that the age is at least 25, we could say the probability that the age is not 12 to 24. So that means that I can rewrite that as 1 minus my ratio. Well, what is the number of participants that were between the ages of 12 and 24? Well, 900. So 900 is the part. And of course, the 3,000 is the total number in the survey. And then I can bring up my calculator and I can put that in there. 1 minus the ratio of 900 divided by the 3,000. And that gives me a ratio of 7/10. So the probability that the moviegoer's age is at least 25 is going to be 7/10. That's my final ratio. This video has been brought to you by Connect the Dots Online Math Tutoring. Before you leave, click on the like button and the subscribe button, and have a wonderful day.